Thank you very much, Rindu and team, for this opportunity to share an investigation we conducted on a really important incident that took place in Surprise, Arizona. We're also going to follow up with experiments that we've conducted and how those results are important to further the understanding of incidents like this. So I'll provide some background and pass it to my colleague, Mark McKinnon, to take us through the incident, and we'll wrap up with experiments we conducted to gain additional insights into energy storage system failures and emergency response. Installations like the one pictured here are becoming increasingly common across the world. These grid-scale energy storage systems offer a low-cost alternative to increasing production capabilities by enabling grid balancing, peak shaving, and load leveling. This is one of the most economical methods to improve grid reliability. With its high energy densities, high efficiencies, and long life cycle, lithium-ion batteries have become the most prevalent technology adapted for ESS globally. The development of lithium-ion battery technology and adoption of this technology into the grid in the form of large capacity ESS has outpaced complete understanding of the hazards associated with the technology, and codes that regulate its use are not able to readily keep up. So lithium-ion batteries are generally very safe, but they have been linked to fire explosion and hazardous material exposure under certain conditions. So to set the stage, a real simple yet effective visual is this thermally induced thermal runaway of a lithium-ion cell. The video shows how quickly thermal runaway occurs and gives a sense of the fire dynamics in an open environment. A video that I'm sure is not new to most people listening here today. So the data presented here shows the rapid increase in temperature at thermal runaway, which can give you a sense of the rate at which thermal runaway progresses. And just as important, the gas composition, which includes flammable hydrocarbon and hydrogen gases. The lower flammability limit and burning velocity are important to understand the hazards as we examine actual incidents and larger applications. In recent years, several fires and explosion incidents involving lithium-ion batteries have appeared in the news and brought increased awareness to the potential hazards associated with this technology. Thermal runaway, which has contributed to all of these widely publicized incidents, and the more we can learn from these incidents, the better we can prevent future incidents from taking place. Of note here is a recent incident where 2 firefighters died in suppression efforts in China. So I'm going to pass it over to my colleague Mark, who's going to take us through the Surprise, Arizona ESS incident investigation.
I'll talk about the Surprise, Arizona ESS incident. A little bit of background. The ESS in the incident was 2 megawatts, 2.16 megawatt hours lithium-ion battery ESS. To put it in perspective, that's about the capacity to power 60 average homes in Arizona for a full day. The ESS was owned by the local electric utility, Arizona Public Service. The batteries were manufactured by LG Chem. The ESS was designed by an integrator called Fluence. It was maintained by contractors to the integrator, a group called Sturgeon. This is important because miscommunications or lack of communication between these different parties contributed to uncertainty and potentially exacerbated the incident. 4 firefighters were seriously injured from the Peoria hazmat team, and 4 firefighters from the Surprise, Arizona Fire Department were held overnight because of suspected exposure to hydrogen cyanide. The ESS consisted of a structure similar to a shipping container with insulated walls that had approximate dimensions of 50 feet by 13 feet by 12 feet. This had 27 racks of battery modules with 14 modules per rack, 28 NMC pouches per module, for a total of 10,584 cells. To put it in perspective, that's almost just over 5,000 potential points of failure, based on an investigation that determined that a single cell pair was the initiating cell for this event. There were 8 HVAC units, as well as an aspirated smoke detector system called the VESTA system, and it had Novec 1230 total flooding clean agent suppression system. All the batteries were charged to 90% state of charge, and everything was operating normally before any indication of an incident was known. So I'll get into the timeline of the incident. In total, the incident from initiation of thermal runaway to the Mayday call where the firefighters were injured was just over 3 hours. These 5 events shown on this slide occurred in just over a minute and show the short period of time between the first indication of a problem and the apparent initiation of thermal runaway. That was followed by an increase in air temperature, and the smoke detector system registered an alarm condition. At this alarm, all of the breakers and contactors opened to electrically isolate each rack, and the HVAC dampers closed to create a relatively closed system. The suppression system was designed to discharge 30 seconds after the smoke detector alarm condition, and it operated as designed and discharged 713 pounds of Novec 1230 into the structure. In an incident involving ordinary commodity storage or in a data center, this would have been the end of the incident. In this case, the batteries continued off-gassing and cascading thermal runaway continued, apparently without a flame, because the clean agent suppression system did not stop thermal runaway and allowed the flammable gases and vapors to accumulate. At 1741, the Phoenix Metro Dispatch received a call for smoke and a bad smell near an electric substation, and the Surprise Fire Department 3 trucks were dispatched. They thought it was a brush fire and were dressed accordingly. At 1744, about 3 minutes later, all communication from the ESS was lost, so there was no more data collected at that point. This shows the air temperature and module temperatures reported prior to that point. It's notable that the alarm condition within the ESS didn't alert or dispatch the fire department personnel, and the closest personnel were not dispatched until 45 minutes after the alarm condition because of a 911 call by a passerby. The ESS was constantly sending out data to Sturgeon and Fluence, and this included these air and module temperatures. Ultimately, this set up the firefighters for having very little information about the incident. The first crew to arrive encountered an O&M contractor from Sturgeon, who told them the structure was storage for lithium-ion batteries. The firefighters, as you can see in these images, the firefighters noticed a white vapor leaking from the door and nearby equipment, and the crew elevated the call to a hazmat operation. About 24 minutes later, the hazmat crew arrived. They saw this low-lying white vapor extending out into the desert, as you can see in the images. One of the firefighters described the smell as burning vinegar, which is indicative of acid gases. The hazmat team defined a hot zone around the ESS structure and entered the hot zone with gas meters and thermal imaging cameras to scan the outside of the structure. They measured dangerously elevated levels of hydrogen cyanide and carbon monoxide in the vicinity of the ESS. These measured levels were at concentrations that were immediately dangerous to life or health, and so they became the primary focus of the hazmat crew. They entered the hot zone 3 times and noticed that conditions in the hot zone were improving over time. There was no emergency response plan from the owner or manufacturer of the ESS prior to the incident, and subject matter experts from the companies were unable to advise the fire department personnel on response actions or meaningful expertise, or provide meaningful expertise on the thermal runaway incident. The hazmat crew and senior fire department leadership developed a plan to make a final entry into the hot zone and render the ESS to a safe state to turn it back over to APS and their O&M contractors. This flow chart indicates what their plan entailed. They would observe the ESS and then enter the hot zone to measure CO and HCN concentrations, to make a determination if the hot zone was safe, if those concentrations were below the IDLH limit. If they weren't, they would retreat and continue to observe the ESS. And if they were at safe levels, they would open the door and check for an active fire. If there was an active fire, they would retreat and allow the ESS to burn. And if there was no active fire, they would retreat and allow the ESS to vent. This was agreed upon by all the senior fire service leadership and was put into action. At about 1950, the visible gas vapor mixture was no longer leaking out of the ESS. And so the hazmat team made a final entry into the fenced area around the ESS. About 5 minutes later, the hazmat team pulled a hose line to the ESS and prepared to open the door. The hose line was there to just protect their retreat or hit a fire if a flash fire occurred. At about 2000 hours, the hazmat team opened the door to the ESS, as you can see in these images. About 3 minutes later, the mayday call occurred. Essentially, when they opened the door, they checked the inside with a thermal imaging camera and gas detectors. Stood there for about 3 minutes to try to determine if there was a fire within the structure. And then at that 3 minute mark, this deflagration occurred. All 4 of the hazmat team crew members lost consciousness during this incident. These are some images from the day after the incident. Shows some of the wreckage, the aftermath of this deflagration event. Both of the doors blew off the structure, and the captain and engineer of the crew were propelled under the fence and into the desert south of the ESS, with the captain of the crew landing about 75 feet from the door. Luckily, all 4 members of the hazmat crew that suffered serious injuries survived, and they're starting to return to duty or return to a sense of normalcy. So I'll get into some of the contributing factors and recommendations that we determined in our investigation. The captain of the hazmat crew was up to date on all required training. He was well educated in lithium-ion batteries and had experience at a fire in an EV repair facility a year prior. So he was probably one of the most qualified in the Phoenix metro area to lead this response. And yet his training did not prepare him for this incident. So our recommendations include adding ESS safety and the basics of vapor cloud dynamics to training at all levels of firefighters. Research also must be conducted to determine the best and safest tactics, and they must be disseminated through the fire service, preferably in an online training program. Until definitive evidence-based tactics can be determined, it's recommended that first responders interact with ESS as if they're filled with a gas mixture above the LEL. Just going into this in a safer mindset. Obviously, with the knowledge of the presence of flammable gases accumulated in the ESS, the hazmat team would have acted differently, and most likely would have avoided these injuries. And so, had sensors been included, we believe that the outcome would have been different. So recommendations are that lithium-ion ESS should incorporate gas monitoring that can be accessed remotely. Also, research must be conducted to determine the effectiveness and limitations of gas monitoring systems. APS claimed that the battery backup for the communication system ran out of power. So this another factor that contributed to the incident. The fire department had no idea what was going on inside the structure during the incident. And so one of our recommendations is to make communication systems more robust so that this communication remains uninterrupted through a conservative estimate of the duration of the incident. Obviously, with an emergency response plan, the Surprise and Peoria crews would have acted differently as well. And although they were provided with an emergency response plan on the scene, the information that provided was inadequate for the response. So owners and operators of ESS should develop an emergency operations plan in conjunction with the local fire service and the AHJ, and make sure that everyone holds a comprehensive understanding of the hazards associated with thermal runaway and lithium-ion battery technology generally. Also, signage should be included that identifies the contents of ESS. When the surprise crew first arrived, they had no idea what the ESS was, and they could have breached the door immediately, and the outcome could have been much worse. Also, the ESS did not have deflagration venting panels or ventilation to prevent accumulation of flammable gases. And it also appears that the total flooding clean agent suppression system contributed to the deflagration because it allowed flammable gases to accumulate within the structure. So our recommendations are that lithium-ion battery ESS should incorporate explosion venting protection as required by consensus standards, as long as that is in coordination with the emergency operations plan. And research must be conducted that includes full-scale testing to understand the most effective fire suppression and explosion prevention systems. And then an additional recommendation that we have, this is the future of the power industry. As demand increases, it's going to be far more cost-effective to develop these ESS as opposed to increasing power production. These images show two lithium-ion battery ESS installations. The one on the left is the one in this incident, Surprise, Arizona. And the one on the right is in Ozone Park in Queens, New York. And they both show about the same length scale. The Surprise ESS had no buildings or homes in the immediate vicinity. They could have been affected by leaked vapors or an explosion blast, but the situation is very different in Ozone Park. Additionally, it took 2 months to completely dismantle the ESS and discharge all stranded energy. The luxury of time may not be available during an emergency incident in a densely populated area. We recommend research be conducted to determine the decommissioning best practices and the role of the fire service in emergency decommissioning. And so I'll pass it back over to Steve, who's going to talk about some of the experimentation that's been done.
So as you could see in those recommendations, there was many that suggested additional research. The incident certainly raised additional questions, and as a result of the investigation, we wanted to follow up that investigation with some research to begin to find answers. So to do this, we partnered with our colleagues within UL's R&D team to conduct installation level experiments. One of the things to also note here is the rapid changes that are taking place within the landscape of codes and standards and test methods for energy storage systems. And we certainly don't have time to get into a comprehensive review of all of the codes and standards, but it's important to note that since the Surprise incident, that there's been updates to the International Fire Code, NFPA 855, UL 9540, and as well as UL 9540A. So just shows how quickly this is evolving. Every opportunity we get to learn more about these hazards and how to mitigate them is able to move all of these processes forward. And these experiments I'm going to talk about are also hoping to contribute to this advancement. So as we talk about UL 9540A, this test method, it's really meant to evaluate fire characteristics of a battery energy storage system that undergo thermal runaway. And this data is important and very useful as we talk about designing these systems, particularly as it relates to deflagration hazards and fire spread hazards specifically. The UL 9540A test standard develops data on the fire and deflagration hazards from thermal runaway and its propagation through energy storage systems. The standard provides a systematic evaluation of thermal runaway and propagation at the cell level, module level, unit level, and installation levels. The data from the testing may be used to design fire protection methods to mitigate against the hazards generated. And here you can see the data generated from each level of testing. And what we've understood over time is there's very little publicly available data for installation level testing that is able to be used and seen. So we wanted to contribute to that gap. The installation level tests included a mock-up initiating energy storage system unit and 2 target units installed within an ISO container outfitted with deflagration protection vents. All the tests were conducted with an identical lithium-ion battery configuration. The initiating ESS unit included 9 modules with a total capacity of close to 29 kilowatt hours. Each mock-up module included 9 mock-up cells. Each mock-up cell was comprised of 30 18650 lithium-ion cells for an equivalent capacity of 99 amp hours in each mock-up cell. The target units were loaded to 1/3 capacity of the initiating unit. And the objectives of this test was to develop non-proprietary UL 9540A installation level data and representative lithium-ion chemistry batteries with and without active fire protection systems, and to develop fire service size up and operational and tactical considerations. So 3 installation level tests were conducted. The first was a baseline test without an active fire suppression system or active ventilation system. Test 2 included Novec 1230, which was deployed 1 minute after thermal runaway upon activation of both installed smoke detectors. And test 3 utilized a water suppression system above the ESS units that had a density water spray of 0.5 GPM per square foot. So we don't have time to get into all of the details during this webinar. However, here is a time history or snapshot that goes through test 2 with the Novec system, highlighting some key events. So you'll see if we start at the top, you've got thermal runaway, and then within 55 seconds, we had smoke accumulation at the second smoke detector. You can see the Novec discharge. You can see the stratification that takes place. And then we have ignition take place just after 28 minutes. After 44 minutes, there was a partial volume deflagration and continued thermal runaway. Once we open the container after 2 hours, you can see the smoke plume that comes out of the open door, and then quickly, in a little over 20 seconds, flash over and flaming from the open door. So for all the details on this, you can see the link at the bottom there, or if you just go to ulfirefighterssafety.org, you'll be able to find this project report and all of the respective details. We will go through some key findings.
So one of the major findings here that's pertinent to the fire service specifically is that room and content fires show a very different gas concentration and composition than an ESS undergoing thermal runaway. So this is important because had the responding crews in this incident known that there was not a content fire but a thermal runaway event, their actions would have been much different. These experiments also show that thermal runaway events generate more severe flammability and toxicity hazards than typical room content fires. And this indicates that training has to catch up to the fact that firefighters might be experiencing far more severe conditions in the future and the present than they did in the past. Another major key finding that still requires some more research, but it's a start. That gas detection can be very effective for detecting thermal runaway, or that a thermal runaway event has occurred, but are not so reliable for ongoing hazard assessment. So the most important function of gas detection in ESS is to identify that, whether a fire is ongoing or whether a thermal runaway event has occurred. The experiments indicate that commonly available combustible gas and hydrogen detectors can signal that a thermal runaway event has occurred, but because the environment generated in a thermal runaway, the gases are much harsher and more complicated than what's typically seen in room content fires. It's far more complicated to do an ongoing hazard assessment. In addition to that, the conditions are very sooty, and so typical gas sensors and sample pumps tend to get clogged very easily. And so some of the advantages, I suppose, are that all of these detectors responded very quickly. And one of the major limitations is that cross sensitivity can diminish electrochemical sensor activity. Also, any halogen gases that or halocarbons that are produced or expelled in the ESS can typically poison these sensors and provide erroneous readings. A major key finding was that the Novec 1230 flooding system was not effective at cooling to the extent that it prevented propagation of thermal runaway. Although it delayed it relative to the no Novec case, it was unable to prevent thermal runaway or exposure to the combustible construction materials. The water spray suppression was far more effective at cooling the container and was able to prevent unit-to-unit propagation, but it did not prevent module-to-module propagation within a single rack. And the deflagration protection system did appear to be effective when partial volume deflagrations occurred. I'll pass it back over to Steve to talk about some of the fire service tactical considerations.
So it's really important as we looked at these experiments that we tried to put it into the context of what can the fire service learn from this. And as a result of the surprise incident and understanding the fire service, there's two key tools that the fire service have access to that we wanted to assess as part of this, that they typically use during their ongoing size up and isolated and understanding the hazard. Those are thermal imaging cameras, which are typically now available on most fire apparatus with responding crews. That gives them the opportunity to essentially look at IR signatures coming off of particular objects. And here you can see that the thermal imaging cameras enable a limited ability to determine whether a suppression system has operated or is operating. So assuming the fire service shows up after activation of any of the suppression systems, it becomes very key to understanding what has taken place before they arrived. And here we saw that you could get some signature out of it, but whether or not it was battery gas, steam, Novec, the camera was not able to determine the difference there. So it's really not a viable tool for determining the nature of the visible vapors. And for that, certainly portable metering becomes important. You can see in the images here that maybe the Novec discharge was able to be seen for a short period of time, but that's likely taking place well before fire department arrival. Also, that sprinkler operation was visible while water was flowing, because of the cooling of the container and obviously the water coming from the container. Next slide. The thermal imaging cameras were not shown to enable evaluating the location or number of ESS units that have gone into thermal runaway. So the results of the 3 experiments show that the wall construction can have a substantial impact on the ability of the thermal imaging camera to assess thermal conditions within the container. These images show surface temperature differences between the interior and exterior wall surface were measured for both insulated and uninsulated construction over the course of the experiment. We purposely put different wall types throughout the container for this particular topic, not knowing all the time what the walls are made of, but in this case they were insulated in the outer parts you can see in the picture, and they absolutely hide any signature of elevated temperature within. And you can see that sometimes that was several hundred degrees Celsius across an insulated wall versus an uninsulated wall, which depending on gaps in insulation could provide very mixed messages to the fire service. Next slide. Another tactical consideration had to do with continuous gas monitoring. And first responders should consider the practicality and continuous monitoring of the interior and exterior gas environment near the ESS. So what we found was the conditions inside the container tend to be very different than the conditions outside the container. In order to get quality readings, particularly as it pertains to an LEL concentration, an opening might need to be made in the container. And certainly because of the proximity that requires and the potential explosion hazard, that is not recommended. Also, as we saw in our experimental gas meters, we saw the same thing in the fire department gas meters, and the soot accumulation clogged the pump style meters very quickly and shut off the capability of continuous monitoring from them. Also, the carbon monoxide and hydrogen concentrations measured were often several orders of magnitude higher than the upper measurement limit of the portable gas meters. And that's really a limiting capability of fire department gas meters and results in needing to have multiple measurement capabilities when responding to these types of incidents. Next slide. And expanding on that, the portable gas meters have limited effectiveness to evaluate the potential for explosive atmosphere within the ESS container. And what we saw was deflagration may occur before flammable gas detection at the exterior of the container would even come close to any of those thresholds. We had meters 1 foot from the container to capture at gaps to allow the measurement of the gases just outside the container. But again, this would really position the firefighters in a dangerous position should a deflagration or explosion take place. And while the exterior gas concentrations were approximately equal to the interior gas concentrations, you would have to be able to do that remotely. But there are other factors that become very important there, whether it's the leakiness of the container, the gaps that exist, the wind, the terrain, all of those are going to play an important role of how to do that practically during an emergency response.